Hello kids, I am back with another video. This time it is about pressure. It is not the pressure you experience in your daily life like having high grades and cramming your physics exam at 1 a.m. in the morning. I know you're doing it right now. It is the pressure that is defined as the magnitude of the normal force acting per unit surface area. In other words, yes, it is the pressure that is found in your physics slides. The pressure is a scalar quantity. We write this mathematically as the following. Pressure is equal to force all over area. The SI unit for pressure is Newton per meter squared, which is given the special name Pascal, in honor of the French mathematician, physicist, and philosopher Blaise Pascal. It is abbreviated as PA. Well, I hope that someone out there will put my surname Tongbo to name something spectacular such as surviving a black hole. In this example that we are going to solve, you can see that pressure is not limited to fluids. Let's read. Jerome weighs 300 pounds. At one particular moment, when he walks, his right heel is the only part of his body that touches the ground. If the heel of his shoe measures 3 inches by 2.25 inches, what pressure does Jerome exert on the ground? So, pressure is equal to force all over area. In this case, our force will be the weight. So, weight all over area is equal to 300 pounds all over 3 inches times 2.25 inches, and the final answer will be 44.4444 pound per inch squared. You may ask me why the unit isn't in pascals. Well, the unit for pressure is in BES, which stands for British Engineering System. If your professor will ask you to convert this into pascals, then you can simply use dimensional analysis for it. I will leave the computation for it to you. Imagine, if Filipinos will have their own engineering system, it will be abbreviated as FES, and the unit for pressure will be Tongbo. Wishful thinking. Now, we are going to head to another equation that concerns pressure. And no, it is not Tongbo's law or Tongbo equation or whatever about me. It is what sometimes experts like me in the future call hydrostatic equation. So P, pressure, is equal to rho or the density times G or the acceleration due to gravity times the height or H. This equation says that the water pressure at any depth h in any pool is given by the product of the density of the water in the pool, the acceleration due to gravity, and the depth of the pool. Let's now solve this problem that is the continuation of the problem we had in our density video. Okay, let's read. After Jerome had finished designing his swimming pool, he is now computing for its water pressure. If the depth is 1 meter and the density of water is 1000 kg per cubic meter, find the water pressure. How do we solve this problem? Pause the video if you want to solve it. To solve this problem, we are going to use the equation I showed you earlier. So, pressure is equal to rho GH. So, our density will be 1000 kg per cubic meter times 9.81 meters per second squared times the height, which is the depth of 1 meter, and the final answer should be 9,810 Newton per meter squared, which is also equivalent to 9,810 Pascal. This pressure at the depth of 1 meter in the pool is the same everywhere. Therefore, the force exerted by the fluid is the same in all directions. That is, the force is the same in up, down, right, left, or in, out directions. If the force due to the fluid were not the same in all directions, then the fluid would flow in the direction away from the greatest pressure and would not be a fluid at rest. Just as there is water pressure, there is also an air pressure exerted on every object at the surface of the earth. This is caused by the weight of all the air that is above us in the atmosphere. This is called normal atmospheric pressure. So 1 atm is equal to 101,325 pascals, and it is also equal to 14.7 pound per inch squared. In this next problem, physics, my favorite subject, will prove to us why we get tired by the end of the day. Let's read. The top of Jerome's head is approximately circular with a radius of 3.5 inches. What force is exerted on the top of his head by normal atmospheric pressure? Pause this video if you want to solve it. Let's first find the area of my head. It is found from area is equal to pi r squared, which is pi times 3.5 inches quantity squared, and the area will be 38.48451,001 inches squared. Next, we find the magnitude of the force exerted on the top of my head by rearranging the equation for pressure. It should be in the form force is equal to pressure times area. Hence, substituting the values, we will get force is equal to 14.7 pound per inch squared times 38.48451,001 inches squared, and our force will be 565.7223 pounds. This is a rather large force to have exerted on our heads all day long. However, we do not notice this enormous force because when we breathe air into our nose or mouth, that air is exerting the same force upward inside our head. Thus, the difference in force between the top of the head and the inside of the head is zero. Now that we have discussed atmospheric pressure, it is obvious that the total pressure exerted at the depth h in the pool of water must be greater than the value we determined in our previous example about the 1 meter pool, because the air above the pool is exerting an atmospheric pressure on the top of the pool. This additional pressure is transmitted undiminished throughout the pool. Hence, the total absolute pressure observed at the depth h in the pool is the sum of the atmospheric pressure plus the pressure of the water itself. So P abs is equal to P naught plus the rho GH. Let's try to solve a problem about absolute pressure. Let's read. What is the absolute pressure at a depth of 1 meter in Jerome's swimming pool? This is the continuation of the problem that we solved earlier. How do we solve that? Pause this video if you want to solve it. The water pressure has already been found to be 9,810 pascals. We can now compute for the absolute pressure by doing the following. P abs, or the absolute pressure, is equal to P naught plus the rho GH. So P abs is equal to 101,325 pascals plus 9,810 pascals. So our absolute pressure would be 111,135 pascals. When the pressure of the air in an automobile tire is measured, the actual pressure being measured is called the gauge pressure. That is, the pressure as indicated on the measuring device that is called gauge. Hence, the total pressure or absolute pressure of the air inside the tire is the sum of the pressure recorded on the gauge plus normal atmospheric pressure. We can write this mathematically as P abs is equal to P naught plus P gauge. Let's now try to use this formula. Let's read this problem. Jerome placed a gauge on an automobile tire. and it wields a pressure of 34 pound per inch squared. What is the absolute pressure of the air in the tire? Okay, let's begin solving this problem by writing the formula for absolute pressure and gauge pressure. So, the absolute pressure is equal to P naught plus Pj. Therefore, the absolute pressure is equal to 34 pound per inch squared plus 14.7 pound per inch squared. Our final answer will be 48.7 pound per inch squared. Finally, allow me to introduce you to Pascal's law. It is stated in this law that if the pressure at any point in an enclosed fluid at rest is changed, the pressure changes by an equal amount at all points in the fluid. The common application of this law is the hydraulic lift. Your professor might show you this equation. F1 all over A1 is equal to F2 all over A2. But I would like to remember it this way by using your professor's notations. Big F all over big A is equal to small f all over small a. The big A and F represent a larger piston, and the small a and f represent otherwise. In the case of the hydraulic lift, it is a device that is capable of multiplying forces. Now, we will solve this last problem, and this concerns the usage of Pascal's law. Let's read. The radius of the small piston is 6.50 centimeters, whereas the radius of the large piston is 34 centimeters. If a force of 3 Newton is applied to the small piston, what force will occur at the large piston? Relax, this is just an easy problem. Let's first compute for the areas of the two pistons respectively. The area of the small piston is A1 is equal to pi R1 squared, which is pi times 6.50 centimeter quantity squared, and the area will be 132.732286 centimeters squared. While the area of the large piston is A2 is equal to pi R2 squared, which is also equal to pi times 34.0 centimeters quantity squared, and the area of the large piston will be 3631.681108 centimeters squared. By manipulating the formula, the force exerted by the fluid on the large piston is F1 is equal to A1 all over A2 times F2, which is also equal to 3631.681108 centimeters squared all over 132.732286 centimeters squared multiplied to 3 newtons. So the force exerted would be 82.0828 newton. Wow! The relatively small force of 3 newton applied to the small piston produces the rather large force of roughly 82 newton at the large piston. The force has been magnified by a factor of 27. See? Physics is that easy. This is Jerome saying, practice makes perfect. I hope you like this video and subscribe to our YouTube channel. Thank you for watching. See you in our next fluid mechanics video.